In this lesson, we're going to focus on the indegree and outdegree of vertices in a digraph. And to start off, we're going to look at two definitions that pertain to digraph and the indegree and outdegree for the vertices. So the first one is the strongly connected digraph. So in a directed graph, a strongly connected graph is going to have a path from each pair of vertices in the graph. So choose any vertex that you want, any second vertex that you want in a digraph. There should be a path that exists there. If there does not, then you do not have a strongly connected digraph. So I have a sample digraph here. So say I choose V1 and V4, I can pass this edge through V2 to V3 to V4, and so there is a path from V1 to V4. Looking at the second definition, a weakly connected digraph is a connected graph if you ignore the directions. So if you simply ignore the directions, then you have a connected graph. So there's no vertice off to the side that's a part of the body of the graph, but not actually connected by an edge to the main part of the graph. So when do you have a strongly connected graph? When do you have a weakly connected digraph? So using this example, I used it as an example to show strongly connected, at least to demonstrate the path, but this is not a strongly connected digraph. And so one of the things to look for if you're trying to determine if you have a strongly connected digraph or not is to see if you can find a pair of vertices in which you can't pass along a path to get from one to the other. So let's look at the extreme vertex over here. I have this labeled as V sub 4. If I start here, can I get to V3? Well, this direction is moving from V3 to V4, so I can't use that edge, but I could use this edge from V4 to V2, and then go from V2 to V3. So I have a connection there. Can I go from V4 to V2? We've just demonstrated that that can happen. How about V4 to V1? Well, I can pass over here to V2, but once I get to V2, I'm stuck and can't get back to V1. So there is a connection that is missing to be strongly connected. And so we can modify this graph and try to build a strongly connected digraph, but as it stands right now, I do not have a strongly connected digraph. Is it weakly connected? If I ignore the edges, is all the vertices connected to the main body of the graph? They are. I don't have any other pieces floating out here. I don't have a vertex or a pair of vertices connected by an edge that's over to the side but not connected in some way to the main body of the graph. And so it is weakly connected, but it is not strongly connected. Again, we can go back through and modify this and create what we need to be strongly connected, but as it stands right now, it is not strongly connected, but it is weakly connected. I want to talk about what indegree and outdegree is for a vertex in a digraph. So the indegree means that the vertex is the terminal vertex for an edge. So that's where an edge stops. So if we look at vertice 3 and vertice 4, this edge starts with V3 as the initial, that's the starting point, and terminates at V4, which is the stopping point. So it's moving from V3 to V4. So the indegree for V4 in this graph is 1 because I have one edge that terminates there. The outdegree is the number of outgoing edges where the vertex would be the initial vertex. So V4 in this graph is also degree 1 for outdegree because it has one edge that moves away from it. Over here looking at V2, the indegree is 2 because I have these two coming in, and its outdegree is 1 because I have this one edge that leaves that vertex. So that's important to understand those definitions before we go and look at this next theorem. The theorem that I want to talk about now is about digraphs and determining if there is an Euler circuit that can be found in these graphs. And so, if the indegree equals the outdegree for each vertex in a weakly connected digraph, then there exists an Euler circuit for the digraph. All right, so we already talked about earlier that the particular graph that I have on the board here is weakly connected. And so, can we determine if there's an Euler circuit with this theorem? We need a way to catalog or organize ourselves so that we know what the indegree and outdegree is for each vertex. So a good way to do that is to create a table and organize ourselves that way. So just list your vertices. So I have 5 vertices in this. They're labeled V1 through V5. So I'm just going to list those off to the side. All right, and so now that I have that across the top, I'm going to write indegree and outdegree. And now we're just going to go through and organize this graph. So for V1, I have a degree of 2 for outdegree. And I have one edge that is terminating there, so I have 1 as the indegree. Going over to V2, again I have 2 out and 1 in. At V3 I have 1 in and 1 out. At V4 I have 1 in and 1 out. And at V5 I have 1 in and 1 out. So looking at the theorem says if the indegree equals the outdegree for each vertex. Well, we don't have that happening. The first 2 vertices here fail that condition. We have 1 and 2, 1 and 2, and so there's not equality between the in and out degrees. V3, V4, and V5 all have what we need to have an Euler circuit, but since vertex 1 and vertex 2 fail, then we're going to fail to have that Euler circuit according to this theorem. If you need a reminder what Euler circuit is, I have that definition on the board here also. It's an Euler path that is going to include each edge of the graph and begins and ends at the same vertex. Now, Euler path can pass the same vertex more than once, but it has to specifically only cross each edge one time. So, according to this theorem, we're not going to be looking for an Euler circuit because our condition did not hold. So, it's not implying that we have an Euler circuit. All right, the next theorem that we're going to look at is very wordy, and it's going to talk about whether there exists an Euler path in the digraph. So, in this, we're given a graph that is weakly connected, which we have, and we're looking for the indegree and the outdegree to not be equal. If there exists exactly 2 vertices for which indegree does not equal the outdegree, and the indegree of, say, the first one is one different between the indegree and outdegree, and then you have a second vertex that has a difference of 1 but switch. So if the first one, the indegree, is bigger than the outdegree, then the second one you want the outdegree bigger than the indegree. If you have this condition where it's 1 off on both vertices but in opposite directions, then there's going to exist an Euler path from the second one to the first one. If this condition doesn't hold, then you don't have an Euler path in this digraph either. So we've already looked at an analysis of the particular one that I have on the board, and we had exactly 2 that differed. But looking at the organization that I have here, we see that indegree and outdegree is off by 1. That's great. On the second one, it's off by 1 also, but it's in the same order. The indegree and outdegree are off by 1, with the outdegree being larger. On V sub 1, the outdegree was larger also. And so we are so close to meeting the conditions of this theorem, and yet again, this particular graph fails the conditions, and so the conclusion is there does not exist an Euler path for the digraph. So we've got a couple really useful theorems in trying to figure out whether an Euler circuit or an Euler path exist, and organizing your information of your graph is going to be useful for analyzing whether these conditions are being met for these theorems to understand whether you have the Euler circuit or the Euler path. Otherwise, you might try the brute force method and just look at it, try every combination you can think of, and so you're losing time in your analysis if you don't have the power of these theorems behind you. You might try to convince yourself, sketch out a little proof about why these two theorems are true. The last theorem that I want to talk about in this video is a theorem that guarantees a Hamilton path. And I think that's exciting because sometimes the Hamiltonian paths and circuits are kind of a little hard to get at, maybe a little more difficult than the Euler path or the Euler circuits. So we need to review what a Hamilton path is first. Hamilton path is a path in a graph that includes each vertex exactly once. And then we also need to define what a tournament graph is. A tournament graph is a complete graph that has had edge directions added to it to make it a digraph. And so I'm going to use the example of K3. And so the theorem says that in a tournament graph with 2 or more vertices, there is always a Hamilton path. So I'm going to use K3 here, and I'm going to start at V1 and add direction away from it. So if this is, say, like a sports team, you're playing the other teams. And so V1 has to play V2, V1 has to play V3. And so at some point, V3 and V2 are going to have to play each other. And so you have to add a direction on who's going to play where. And so we'll just, without loss of generality, choose V2 playing V3 at V3. All right, and so now I have these directions. So do I have a path that is going to include each vertex exactly once? So I start at V1 and I can move to V2 and I can end at V3, and so I have included each vertex exactly once, and I visited by using 2 edges in this digraph. All right, I'm going to leave you with a challenge. If there is no simple circuit in your tournament graph, what happens to the tournament graph and the Hamilton path? Cheerful calculations.